Okay, so next presentation, it's a little bit different now than Christian's, but I was thinking, how can I connect to a previous presentation from Christian? And it's really about interaction mode, I guess, in your canvas. So the work I'm presenting was done by my PhD students, and it's one of his studies, and his PhD topic is about nonverbal interaction with robots in education. So he is experimenting with different nonverbal sounds and how they can be integrated into educational scenarios. And in this particular one, we developed a quiz application for the Pepper robot, which happens in the classroom, and there are two teams. And I don't know if you know this quiz game, probably from TV, where there are two people and there is a question. And if you know the answer, you press the buzzer. And if you are the first one to press the buzzer, you are the one that can answer the question. And then you gather points. So we kind of translated this idea to an interaction with robot in educational scenarios. And what he tested in this particular study was if this interaction through the buzzer, how this affects motivation and engagement, because we know that interacting with robots in general is very motivating and engaging compared to screen-based media. But we wanted to see how the sound-driven turn-taking in this robot-assisted quizzes enhances motivation and engagement. So this PhD student cannot be here, but I'm basically presenting part of his PhD work. So if you have more questions about this, especially about technical things, you should contact him, because I honestly have no idea about machine learning for non. I mean, I have some idea, but not for what he has done in detail. So I will keep this short. The introduction, I told you about the scenario. The motivation for his research is to see how we can integrate social robots in education, how we can combine this with gamification approaches and nonverbal sound recognition, and how sounds as nonverbal elements can be part of the interaction with robots in education. So he has done a literature review and identified some research gaps. And his main R&D objective is to design, develop, and evaluate a system that combines gamification, social robots, sound input to enhance student engagement and motivation. So the main research question for this study was to see how sound-driven first responder detection, so this buzzer is like a first responder detection, in robot-assisted quizzes impacts engagement and motivation of students interacting with the robot compared to a sequential interaction, which is pre-programmed way of you answer first and you answer second. So there is a sequence of who can answer when. So he wanted to compare this. His theoretical foundations for the interaction design are based in self-determination theory by Deci and Ryan. So focusing on autonomy, competence, and relatedness, social relatedness. The gamification design, what he used here was the Octalysis framework. So trying to balance the positive and negative elements in gamification, like, for example, time constraints, some surprise elements, and so on. And for the results interpretation, what he chose was the arousal law by, I don't know how to pronounce Yerkes and Dodson, this name. I don't know, you're a psychologist, maybe you know this law. I found it interesting that he found it's actually a little bit like a flow theory background, which basically says that the higher it's like the curve that says that the higher the if it reaches the peak, then there is a stress and a tendency to performance to drop down. But a little bit of arousal is quite good for the performance to actually spike. So it's a question of finding the sweet spot of having the optimum level of arousal and then the performance going up. So this is the architecture that he designed for this quiz game with the buzzers. So we have two teams, we have two buzzers, and he trained a model which runs on the Pepper robot or on a server outside of the Pepper robot. But he trains the model to recognize the buzzer sounds and also the localization of the sound. So the robot can recognize which buzzer was pressed first. The buzzers have a little bit different sounds. And then the robot can react on this and can say, okay, I recognize that this buzzer was pressed first. So the group A can start answering the question. And then there's this whole gamification framework in the background where students get points. There are different levels. So we have different questions for different levels. They get some points, they get some badges, and their time limits. So different elements from the Octalysis framework. So he used random forest mechanism for this first responder detection. Yeah, he used basically, we have he used Kotlin to create the application for this. And this all runs on a server, as you can see here, Python based, and he is using WebSockets to have this server Pepper communication. And also one more important thing is that in the output layer, we have the different gamification elements, but we also have the different gestures and outputs from the robot. So the robot makes happy gestures if there's a correct answer, or very sad gesture if the answer was wrong. And there's also some verbal output and some melody, some music played by the robot as well. So there's like very multimodal, many different elements going on. So he's trying to make it as engaging as possible. So this is the game flow. The game starts, then the Pepper Robot presents the game rules. Then Pepper Robot, as you know, has a tablet. So the questions are appearing on the tablet. When we use this in the classroom, we also mirror what is on the tablet with the screen. So the students can see it here, but if you sit further away, you can see it on the screen as well. So then Pepper presents the questions. If the team knows the question, they press the buzzer, and then this all goes on until all the questions from different levels are answered, and then points are collected. Pepper makes some music and gesture for positive and sad for negative. And yes, this goes on until all the questions are answered, and then the game ends and the results are displayed. So each team sees how many points they got and which levels they reached. So this is the game user interface. So you can see it's like a multiple choice quiz with a question for different answers. And then the students can say it's answer A, B, C, or D in this way. I'm saying this because he also designed other versions of this quiz where the students can verbally say answer A, B, C, but they can also clap or do something else, because he's exploring the different inputs also, not only the verbal, but non-verbal inputs as well. But that's another study. And yeah, you can see he designed some badges for this, some points. So this is what is displayed in the end, and each team can see their progress or their outcomes. So I hope we can see the little demo of this. It's in German. Okay, so just that you see, it's not the whole game, but it's like we have these two teams, and then they press the buzzers. So this study that he did to assess this was an experimental study with an experimental group that used the buzzers and another control group that used the sequential turn taking, which was pre-programmed. He had 60 students in a programming course. In each condition, there was a blue team and a green team, so they had different buzzers. And there was a 60 minutes quiz session about machine learning concepts. And what he did was a post survey with different matrix where he measured competence, immersion, flow, tension, annoyance, challenge, positive and negative effects. So these are all elements from the game experience questionnaire. And these are the results. So in general, the game experience questionnaire includes different dimensions, and these are all the dimensions from there. And so he compared the experimental and the control group. So when we were designing this, we of course hoped that the buzzer quiz game would increase the motivation and engagement, that it would have a positive impact. But what we found out was exactly the opposite. So yeah, you can see that, right? So the control group had higher competence, higher immersion, higher flow, lower tension, lower challenge, lower negative effect, and higher positive effect. So exactly. So what? So now he tried, we have the subscales here. You can see this here. The buzzer is the dark blue and the sequential one is the green box. So it's just, and what he also did is the qualitative data. He also, the interviews with students afterwards. So he wanted to know how they experience both conditions. So he got all these, you can just have a quick look at the comments from the students. So he analyzed all this. He asked a question, what did you like most? How could we improve? And how motivating, engaging, and enjoying was the game? And so I think his interesting interpretation of this was from this arousal theory perspective, where he said that including the buzzer, based on the data that he has, added too much arousal. It was just too much arousal, too many elements. The students were too much under stress. They knew they have to press, and they didn't, also what the students said, they didn't know if the robot would recognize this in a proper way, if it was fair enough, if they really, because some students claimed we pressed first and the robot didn't recognize it, recognizes the other. So they were not quite sure if there is fairness in the system. And because of this, the results were the opposite of what we expected when we started designing the game. So he now follows up on this, and also in his PhD thesis included this fairness element and the arousal and how to balance this so that when we add nonverbal sound recognition in interaction scenarios, it can still, how can we do it on the design level so it can be perceived as fair and not too stressful, the arousal doesn't spike too much, so that the experience is positive and the performance is also optimal. So this is his this discussion, and his conclusions from his experiment is that the sound-driven interaction created more competition and engagement, but the noise misdetections or the perceived misdetections may lead to frustration and reduced trust. His insight is that reliability and predictability are quite essential for positive user experience. So to trust the robot, you need to know that the robot is actually predictable and fair. And he discusses some limitations, small sample, of course, the training with random forest, the ambient classroom noises that were not fully detected, and the implications for future work is to the design question, how to reduce the arousal spikes, and also how to create more fairness or justice, or reduce the injustice cues that come from the unpredictability of the robot's behavior. So that are his references, and that's it. And if you have any questions, I can try answer them. Yeah.
Okay. So I wanted to go to the technological or technical details. What I noticed, for start, I don't think that the negativeness that you mentioned in the qualitative, in the quantitative outcomes are necessarily bad.
Yeah, yeah.
They're always good in the benefit of reason.
Yeah, yeah, true.
What surprised me a bit is the slide afterwards, the qualitative one. And I roughly read the argumentations there, and I couldn't find it. If I take for fun and enjoyment, I mean, you can hardly find the hints that would lead to the negative results that you get in the other one. So it kind of surprised me. I mean, so this is one thing. The other comment that I have, and I go back to yesterday's session, the doctoral session, about the too many variables. I think that, and this is the risk, this is the word of the risk, continuing my talk. I mean, when I speak about educational spaces with ingredients and IoT devices, the same that you are using here with the tactile buttons, I mean, you run the risk that you are checking a bit more than the robot.
Yeah. That's true. There are many variables. Yeah. Okay.
But really, I mean, it's a wonderful work that you have done.
Yeah.
I'm sure that this.
And you know the student, you met him, Rezaul Tutul.
Okay.
You remember him
Okay,
when he was starting working. Yeah.
And I'm sure that with the refinements and everything, I'm sure that those negative results would be drastically improved.
Yeah.
But,
so for me, it seems that the negative results maybe had not had to do with the design itself, right? But really just with the technical.
Of the system.
You know, it's like just like the technology acceptance.
Yeah.
The utility in the moment that it doesn't recognize exactly. And then you get a sense of
frustration.
unfairness.
Yeah.
So that's It's like that now they're only focused on now that was not fair. So I think that it's just like more like a technical problem. And then it could be interesting to see
if it improves.
And I think it's actually a nice idea to do like a comparison. Between just a robot and because if I understand correctly, the control condition. It was not really like the game, right? In the sense of, the pressure.
Exactly. You knew you can answer now, and then you can answer the second round.
Right.
Yeah.
So, and actually, you could do like for both of these conditions, you can do with robot and without robot, like 2 by 2.
True.
So the robot would say, now it's your turn.
Now
it's your turn.
And
then you can also have like a system without a robot that detects.
That's a good idea.
I think
it could be a nice study. Yeah, true.
And a short comment. If you go back to the flow chart. That's one as a computer scientist.
Okay.
There is the processing, which is the rectangle or the.
This one?
Yes, exactly. There is the processing, the starting phase, which is the elliptical, the start and the end. That's nice. There are the processing, which are kind of rectangles. But things that concern inputs or outputs should be, in English, it's a parallelogram.
Okay. This one.
Yes.
Yeah, you're right.
Okay, but
I will, Good feedback.
But again, and I sit on the shoulders of people much bigger than I, Judith Doring. Negative results are not bad.
At least it inspires him to think further. Why?
I also wanted to ask you, this is a game flow for Pepper robot. But this could also
be any
applied in the other robots.
Now robot.
And you can also experiment and see how it went. If it went better
with another robot. True.
And because I don't know, I'm not using these robots, but maybe also the way that they, interact or the way that they respond to such an activity would be different and maybe would be better, I don't know, perceived by the students.
Could
so
be.
Maybe this we can understand the bad, but the other can understand it much better. I don't know, since you have more than one.
We could
you can also
try with another one.
If you have, try to use this kind of activities with this robot and not the other.